All right. First problem says, okay, so first it tells us to balance the following redox reactions under the medium conditions stated. So the first thing I need to look for is I need to know whether it's acidic or basic, because step 7 is all hinged upon, is it acidic or basic? So now the way I work these problems is I'm going to divide this into two halves. And that's not quite half, but it's close enough. So you want to draw a line on your paper, and we're going to do one half reaction on the left and one on the right. And then actually leave yourself as a little bit of space. And then we're going to save the spot at the bottom where we're going to add everything up. Okay? All right. So the first thing I'm going to do is I'm going to separate problem. Step 1 says write the unbalanced equation for the reaction in the ionic form. Well, fortunately for us, that is right here. This is step 1. It's the unbalanced equation written in the ionic form. We know it's unbalanced because, well, I have negative charges on the left and none on the right. And I also have only one iodine on the left and 2 on the right, 2 oxygens on the left and only 1 on the right. So I know that this is unbalanced. The second step is going to be to separate this into two half reactions. So this is where I'm going to use my two sides. I'm going to break apart the like species. And I'm going to go ahead and drop the phase states because at this point they're not going to have really any impact on the how I mass or charge balance. They're just, it's extra stuff I'm writing. So I'm not going to include the phase states. And then I'm going to go ahead and write my second half reaction. So I'm combining the like things. So let's use different colors. Iodine becomes iodine, or iodide becomes iodine. And then we have the nitrite becoming nitrogen oxide, monoxide. Okay, so that's where those came from. The one half reaction and the other one. So iodide is never going to form nitrogen monoxide, right? So you're going to keep like species together. All right, the third step says to balance each half reaction for the number and types of atoms and charges. Okay, so that's the first thing I'm going to do. And I'm going to do that by just mass balancing and charge balancing. So in this case, I have 2 iodine on the right, and I know I need 2 iodide atoms on the left. So I'm going to put a 2 coefficient. Now the next thing I'm going to do is I need to charge balance, and you can only add negative charges by adding electrons. So I'm going to add 2 electrons to the right because I have 2 negative charge on the left. So now I need a 2 negative charge on the right so that they are equal to each other. Okay, and then the next part of this says, if needed, I need to add water to balance out any oxygen atoms. Well, in this case, there are no oxygen atoms, and so this one is good to go as far as step 3 is concerned. Over here, for this half reaction, there's 2 things I see. You might be tempted to add an oxygen, like a coefficient on the right to balance out this oxygen, the 2 oxygens on the left, but that's where this rule is important. What I'm going to do is I'm going to take and I'm going to add 1 oxygen. One water, and I'm going to leave myself some space. I'm going to add 1 water on the right-hand side to balance out the extra oxygen on the left-hand side. So now I have 2 oxygens on the left and 2 on the right, but when I added the water, I also added hydrogens, and so now I'm going to add 2 protons to the left to balance out the 2 hydrogens that came when I added the water. Now, as far as adding the electrons, because I need to balance not only the atoms, but the charges, I have to look at my total overall charge. I have 2 protons on the left plus a 1 minus polyatomic ion becoming 2 neutral molecules. Now on the left hand side, 2 plus a negative 1 gives me a positive 1. And the only way to make positive 1 equal 0 is by adding something negative to the left-hand side to cancel it out, right? Because then 1 minus plus 1 plus becomes 0. So I'm going to go ahead and rewrite, and then I'm going to give you a hint. Because there was two ways to do that. The way that I did it was I looked at the overall charges on the left and the right and tried to make them balance each other out. However, if I look on the left-hand side, I added those 2 electrons to the right-hand side, which means this is the oxidation. I could not have added 2 electrons to the right-hand side in the second half reaction on the right, because that would also be oxidation. So I knew I could have made a prediction that this was going to be a reduction. Okay, oxidation and reduction, meaning the electrons were going to be gained on the left-hand side. Okay, so I've done everything. And I wrote 2 in front of that. That should just be 1 electron. I got ahead of myself. Okay, so 1 electron, 1 negative NO2 molecule, 2 hydrogens gives me a neutral left side balanced by a neutral right side. All right, so that's step 3. Step 4 says if the oxidation and reduction half reactions contain different number of electrons, you're going to multiply one or both to make sure that the number of electrons are equal. So in this case, I have 2 electrons on my half reaction on the left and only 1 on the right. So just to be consistent, I rewrite the equations. It does not take me any extra time to rewrite the equations so that whenever I go back, I can make sure that I have accounted for every step. So because there's 2 electrons in the oxidation half reaction, I need 2 in the reduction half. So I'm going to multiply the entire half reaction on the right-hand side by 2. So everything is going to double, giving me 2 electrons, 4 protons, 2 NO2 minuses, 2 NOs, and 2 waters. Okay, so that's step 4. Step number 5 says add the 2 half reactions together and balance the final equation by inspection. The electrons on both sides must cancel out. So now what I'm going to do is I'm going to cross out anything that's going to cancel. So 2 electrons are going to cancel. I don't have any other similar species in the 2 half reactions. Everything else is unique. So now I'm going to add up the left and add up the right. So this is where I'm going to add. This is step 5. So I'm going to start on the left-hand side, and I probably should have been an accountant because I like to document that I am adding the right things to the right side, because when I was in your shoes, I made mistakes like that when I was being too hurried. Okay, so now we are going to make sure, we need to, step number 6, verify that the equation contains the same type and numbers of atoms and the same charges on both sides. And so in this case, I have 2 iodines, 4 protons, 2 nitrogens, and 4 oxygens. So I have 2 here and 2 there. So it's mass balanced, yes. Now I need to look at charge balance. I have a 2 minus here, plus a 4 plus there, and 2 NO2s equal to neutral plus neutral plus neutral. Right? Remember those oxidation states. So 2 minus plus 4 plus 2 minus also equals 0. So 0 equals 0. So this is also charge balanced. So it's good. Now, the last part says if the redox reaction is an acidic medium, no more steps are required. Okay, so we're going to just stop there. So my final equation is the same thing I wrote up ahead, but I'm going to rewrite it and put step number 6. Did I do that right? Oh wait, this should be number 7. Number 6 was this. Okay, and I'm going to go ahead and highlight it, and then I'm going to stop this video and give you a chance to think about it, let that sink in. Remember, these are the rules for an acidic equation. As you may guess, the next one is going to be a basic equation. So it's going to have a little extra step, but it's not going to be any harder because everything else we're going to do up until that part is going to be very similar.